welcome to the 22nd lecture of this course. So, today we are going to carry on our discussion about push down automata. We will first see the formal definition and what does it mean for a push down automata to compute a string, and then we will look at the exact computation of a push down automata using an example. So, first let me define what a push down automata is. So, a push down automaton in short PDA is a 6 tuple Q sigma gamma delta Q naught F, where essentially the symbols represent the usual things except for gamma, which is the stack alphabet. So, Q is the finite set of states, sigma is the input alphabet, gamma is the stack alphabet, delta, which is a map from Q cross sigma epsilon cross gamma epsilon to um, 2 to the power Q cross gamma epsilon is the transition function. Okay. Q naught is the start state and F is the set of accept states. Okay. So, let me talk a little bit about the transition function, because that is the thing which is different from that of a epsilon NFA. So, the transition function takes the following as input. Okay. So, if you look at it, firstly it takes a state as input, it takes a symbol AI in sigma epsilon as an input. Okay. So, basically this is the input symbol, and it is reading a symbol X in gamma epsilon. Okay. So, this is input symbol, and this is symbol at the top of the stack. Okay. So, it is taking these things as input, and what it is producing is, it is producing pairs of the form some q comma y, where q is the new state that you go to and y is the symbol with which you replace x. Okay. So, this guy is in belongs to capital Q, and this guy belongs to gamma epsilon. So, what do I mean by pairs? What do I mean when I say pairs? Okay. So, it is not that it is just, it can output just one state comma stack symbol pair given a triplet of the form. So, let us say here the state is P. So, given let us say P, A, I and X, it can actually output multiple Q comma Y. Okay. So, this is because of the non-determinism. Okay. So, due to non-determinism of the push down automata, there can be multiple transitions on the same tuple, let us say P, A I and X. Okay. So, this is where, this is why we say that it is an epsilon NFA, a non-deterministic finite automata, because as I said that there can be multiple such pairs. Okay. So, this is this transition is denoted as from state P you are going to some state Q on reading the bit AI, and the stack symbol X gets replaced with Y. Okay. So, this is how a transition is denoted. So, in the case of finite automata, we had just from P to Q on a symbol AI, but now we have this additional thing to represent how the stack changes, the behavior of the stack. Okay. So, now let me define the computation of a push down automata. So, a PDA, so let us call it P, equals Q sigma gamma delta Q naught and F, is said to accept a string W in sigma star if there exists there exist three things. Firstly, there exists a sequence of symbols A1, A2 up to AM, each belonging to sigma epsilon. Okay, so there exist m symbols belonging to sigma epsilon. There exist states R0, R1 through Rm belonging to Q, and strings S S0, S1 up to Sm belonging to gamma star. Okay. So, essentially there exists, so we assume three things, A1 through Am, which are symbols from in sigma epsilon. There exists states R0 to Rm, and there exists strings S0 through Sm over gamma star. Okay, so these are strings over the tape alphabet. So essentially, intuitively, what these M states mean is that the PDA, on when it receives the string W, it basically accepts a W in M steps. Okay, where at each step it is reading AI. Okay, so AI can be empty also. At each step it is going from a state Ri minus 1 to Ri, and at each step the contents of the step, the contents of the stack is basically Si. Okay. So, whatever string that is contained in the stack from top to bottom is Si. Okay. So, let me just rephrase what I just said. Such that firstly, W is the string, the concatenation of the symbols A1, A2 up to Am. Okay, so, whatever input W that is given to us, it is nothing but the concatenation of the symbols that I read at each step. Okay. So, again note that some of these can be empty. So, it is not that the length of W is M, the length of W is something that is less than or equal to M. Okay. Second is the initial condition, that is, so what happens at the beginning? So, at the beginning we have R0 equals Q0 and S0 is empty. Okay. So, at the beginning the stack contains nothing. Okay. So, this is the initial condition. Third is the transition condition. So, we write the transition condition as, for all I, what it does is, if delta okay, if Ri comma y is contained in delta R I minus 1 comma ai comma x, then S I minus 1 is xt and Si is yt for some t in gamma star, and x comma y in gamma epsilon. Okay. So, this is the transition condition. So, essentially what this is saying is that look at some I between 1 and m. Okay. So, this is I in the set 1 through m. Now, suppose if I look at delta Ri minus 1 Ai and x for some x, x can be any symbol in gamma epsilon, and if that set contains a pair, contains the pair Ri comma y, then the stack in the I minus 1th step should have had x at the top followed by some string y, and in the ith step it got replaced, that x got replaced with y, and the remainder of the stack remains the same. So, it was t earlier, it remains t. Okay. And this essentially means that the computation moves from the Ri minus 1 from the state Ri minus 1 to the state Ri. Okay. So, this is what transition means. And when do we accept W? So, we accept W if finally the last state is the accept state. Okay. So, if Rm is, it belongs to F. So, again if I want to give a pictorial representation, so then if I look at the stack before the ith step, it contains t with x on the top, and after the ith step it moves to t followed by y at the top. Okay. So, now enough of definitions, let us look at a example. So, what we will show is something that will prove that the power of push down automata is more than the power of finite automata. In other words, push down automata can accept non-regular languages. So, example. So, we will construct a push down automata for our for the popular language 0 to the power n, 1 to the power n. Okay. So, this is a language which has helped us in many places. So, first it helped us to show that to construct the first example of a non-regular language, to show that a language is non-regular. Then we showed that context free grammars are able to accept this language, and today what we will show is that even a push down automata can accept this language. Okay. So, what is the idea? I mean, how does the push down automata work? I mean, how does it go about accepting this? So, what we will do is whenever we will have a push down automata where whenever it reads zeros, the push down automata will be at a certain state, okay, let us say at some state p, and it will push some symbol onto the stack. Let us say it will push the symbol A, capital A, onto the stack. So, for each 0 that is being read, it will keep on pushing zeros, and then the moment it sees the first one, it will move from the state p to some other state, let us say q, and it will start popping out A's from the stack. Okay. So, it will keep on doing this, and finally, if when the input is completely read, if the stack becomes empty, whatever it was at the very beginning, then we say that the push down automata has correctly I mean the input that was given is of the form 0 to the power n, 1 to the power n, because the number of A's pushed matches the number of A's popped when the string is completely read. Otherwise, we will say that it is not. Okay. So, we will look at some examples. So, here we will use, here we will construct the push down automata. So, we have a state, let us call it, this is our start state, let us call it Q0. From Q0, I go to a state Q1 on reading epsilon, and I push a symbol hash onto the stack. So, let us try to understand this. So, this transition means that I do not read any input bit, okay, I just see epsilon, but what I do is that by reading nothing from the stack, I push hash onto it, okay, some symbol. So, basically this symbol will be used to check whether the end of stack has reached or not, okay, because finally we need to check whether we have reached the end of stack. We will use Q1 to push A's, okay, to read 0 and push A's. So, on Q1 what we will do is that if I see a 0, I will push an A onto the stack. So, this means pushing an A. Now, from Q1 I go to a state Q2, okay, or Q2 I will use to pop out A's. So, on Q2 if I see a 1, I will pop out A, and then finally what I do is that again without reading anything, I will check if the last symbol is a hash. If it is a hash, I just let us say pop it out, it does not matter, and I reach a state Q4, which is also my accept state. Okay. So, now the only thing needed is to label this transition. So, when will I go from Q1 to Q2? So, I just do that non-deterministically. So, whenever I am at a state Q1, I will non-deterministically do one of the two things. Either I will check whether the next bit is a 0 or not, or without reading any symbol and changing anything on the stack, okay, the stack remains as it is, epsilon to epsilon, I just go to this. Okay. So, this essentially means that non-deterministically I am trying to see if the next symbol is a 0 or if the next symbol is going to be a 1. Okay. That is all. So, this is a PDA for the language L. Okay. So, now let us try to look at some example to see how the PDA behaves. So, let us take W equal to a string 0 square 1 square. Okay. So, on this string what we will do is we will construct the following table where I have symbol red, okay. Just write it clearly. Then transition used, current state, and stack contents. Okay. So, these are the things that we will try to see. So, initially at the beginning we do not have anything. So, the automaton is at the state Q0, and the stack has nothing on it. So, it is empty. So, this is the initial condition. Now, which symbol will it read? So, first if you look at the automaton, okay, first it has to go from Q0 to Q1, it reads nothing. So, it reads the symbol epsilon, it uses the transition epsilon comma epsilon to hash, okay, it pushes in hash onto the stack and it goes to state Q1. So, now the stack has hash on top. In the next step, it is going to read the first 0. So, it will read 0, it will use the transition 0 epsilon to A, it stays at the state Q1, okay. And now it has pushed A onto it. So, now the stack has, if I just want to write it as a string, it has A hash, A on top and hash below it. It reads the next 0, sees, uses the transition again epsilon going to A, uses, stays at the state Q1 and now the stack has A hash. Okay. Now, the zeros are exhausted. So, now what we will do is that we will use the transition epsilon comma epsilon going to epsilon. So, we will not read any input bit. So, the symbol read will be epsilon. It moves to state Q2, the stack remains unchanged. In the next step, it sees 1, it uses the transition 1 A to epsilon, which means that it is popping off A and it stays at state Q2. Okay. So, the current condition of the stack is A hash. Then it again reads a 1, it uses the transition A going from A to epsilon and it stays at the state Q2. Now, the stack has hash on it. Okay, now, the ones are read. Now, it can again without reading an input symbol, it can use the transition epsilon, hash going to epsilon, move to the state Q3 and basically accept. Okay. So, now if I concatenate all these, I get W, which is 0 star 1 star, which means that this guy gets accepted. Okay. So, now let us look at a similar table for a string which is not accepted. A string W which is 0 square 1. Okay. Suppose if I try to accept 0 square 1. What happens? So, initially again I have Q naught and epsilon. On reading epsilon, I use the transition epsilon going from epsilon to hash and push, move to state Q1 and push a hash onto the stack. Then on reading 0, I use the transition 0 epsilon to A Q1 A hash, again I read 0, again I use this transition and go to A hash. Now, I use the transition epsilon to epsilon, move to state Q2, stack remains unchanged. Next, I read a 1. So, it is 1 comma A gets popped out. I remain at state Q2. okay, and the stack contains a hash, and here my at this step my input is exhausted, okay, I do not have any more bits to read. So, I cannot use this transition to go to Q4 from Q, so this should be Q3. I cannot use that because now my top of the stack contains A, so I cannot use that transition. So, I am stuck at the state Q2 and I cannot accept, okay. So, because of this, this string does not get accepted. And it is non-deterministic, okay. So, this is just one computation path that I showed. You can also check that there may be other computation paths, you can try out other computation paths and you will be able to see that on none of the computation paths will you actually reach the accept state. Okay. Another example that you can try out is for the string 0 1 square. For 0 1 square, what you can see is that although you are able to reach the state Q3, but when you reach the state Q3, you will not be able to exhaust the entire input. For example, if I have the string so if I have the string 0 1 square, then if I read the first 0 and a 1, I will be able to go to state Q3 because 0 1, but then the input is not completely exhausted, which means that W will not get accepted. Okay. So, I will stop here today, and in the next lecture we will look at some more examples of languages which are accepted by push down automata. Okay. Thank you.